In this video, we're going to take a look at using the multiplication principle or the multiplicative inverse property to continue to solve single variable equations. Okay, so when we're looking at the multiplication principle or the multiplicative inverse, what I want you to think about is, well, in shortcut, you're thinking flipperoo, or you're going to flip this to write the reciprocal. And the reciprocal, like I said, is just the flipping of it. But basically, the multiplicative inverse is you're looking at what number would I multiply this number by to get to 1. And when we get to our next lesson, the second part of this lesson, you'll see why that's important. But what I want you to look at here is the reciprocal is going to be 1 over, and it could be, I could write -7 here, or negative up here with the 1, or negative up front. But basically, it's taking -7 and flipping it, writing it as a fraction. The reciprocal of -7 is going to be -1/7. The sign stays the same. We're not going to lose the sign or flip the sign, switch the sign. We're just flipping our number, writing it as a reciprocal. The next one here, the reciprocal for 8 is 1/8. And I want to go back and forth and kind of compare something here. If I would go to multiply 8 times 1/8, I could write 8 over 1 here. 8 times 1 would be 8, and 1 times 8 would be 8. I'd end up with 8 over 8, which would be 1. Or I could look at this as diagonally, these two numbers would reduce, and my answer would be 1. That's what makes this important. If I did the same thing back here with the -7, I could write -7 over 1. I could go ahead and reduce diagonally here. A -7 would reduce with the -7, and I'd end up with 1 again. That's what makes this important. Now, I'm not so concerned about carrying out that multiplication and reducing and so forth right now. I just want you to understand, I want you to be able to follow how do we find the multiplicative inverse. But the fact that these two things multiply together and our outcome is 1 is huge going forward. Okay, so looking at a number like -1, what number times -1 would give us an outcome of 1? And that would be also a -1. I could write that as over 1, but no matter how I did that, I could multiply and I would come up with 1 here. So -1 is kind of a unique one, because -1 over 1 is the same as -1. When I have something like 5/4, the reciprocal of this, I would have to write 4 over 5. Now keep in mind, you see how diagonally these would reduce. If I was going to go ahead and multiply them, they would reduce diagonally to have an outcome of 1. Here I need to have a 2 up here, and this would also be negative, because a negative times a negative would give me a +1, and then my 2's would reduce. This here I'm going to leave as -8 over 3, because the 3's would reduce, the 8's would reduce, and I'd have a negative times a negative, which would give me 1. I'm not actually writing that out because that's not my whole point right here, but I want you to recognize our multiplicative inverses are just flipping and keeping the sign. The signs do not change. So how do we use that going forward? Now, I'm hoping everybody can just kind of bear with me on these next 3 problems that we're going to work through, because I know there's kind of a shortcut that you can work through, and even I catch myself that I'm not exactly demonstrating the property the way I want to. But what I want you to think about here is we're going to use this multiplicative inverse, because with our algebra, our goal is to try to work through a series of steps so that we're isolating that variable. We're trying to get that variable by itself. So I want you to think about using the multiplicative inverse. In other words, what do I multiply? The connection here is multiplication. And so what could I multiply to get this number here in front of that variable to be 1? Because really 1 times x would be equal to x. And so I want to get rid of this 6. So I could multiply both sides by 1/6. Because when I do that, I could write this 6 over 1. I could see that my 6's would reduce diagonally here, and I'd be left with 1 over 1, or 1 times x, so that x would be isolated now by itself. That's our whole point. I could write that 30 over 1. 6 goes into 30. That would be 5 times, and so our solution would be x is equal to 5. Here I'm trying to get the m by itself. Happens to be on the left side of the equation again, but trying to get the m by itself. And I have to remember I have to multiply something in order to get this 4 to reduce. So if I multiplied by a 1/4, looked at this as 4 over 1, these two 4s would reduce diagonally and I'd have m by itself. But if I multiply the left side by 1/4, I have to multiply the right side by 1/4. So I'd end up everything eliminating other than the m on the left side, so I'd have m by itself equal to negative 7/4. Using the multiplicative inverse here on the next one, I've got the variable on the right side, so I'm going to have to multiply the right side by something to get the p by itself. And so I'm going to need to multiply by negative 1/9, that's the multiplicative inverse. That would mean my 9s would reduce, and negative times a negative gives me positive, and so I'd have p by itself. But if I multiply the right side by negative 1/9, I need to multiply the left side by negative 1/9. 9 goes into 72 8 times. A negative times a negative makes that positive, so we'd end up with a positive 8. Moving on to this next one, it's really kind of tempting to take a total shortcut here, but this is like a negative 1 here. And so I need to multiply this left side by a negative 1, right side by a negative 1. Negative times negative gives that positive x, and I end up with equal to positive 10, because a negative times a negative gives us positive here. I'm going to go ahead and rewrite this problem and rewrite negative x is equal to negative 10. Another way to look at that is I could divide each side by negative 1 to get the same response. A negative over a negative gives me, again, that's like a negative 1, so that would reduce, and x would be equal to positive 10. So either way I get there. But what I want to point out is that when you start out with something like a negative variable, you don't want to know what negative x is, you want to know what x is. And so I need to get rid of that negativeness and that left side. So you could either multiply or divide both sides by negative 1, which is going to change the signs on both sides. So that's just kind of a trick to try to clear the negativeness away from a variable. Okay, over here, there's really no shortcut I could take on this one, because I'm trying to get y by itself. It's over here on the right side. I'm trying to get y by itself. I have to reduce this negative 5 with a negative 5 down here, and this 6 with a 6 up here. So I'm multiplying by the reciprocal. That's why the reciprocal works. It's going to eliminate this coefficient, is what we call this number. So if I multiply the right side by 6 over negative 1/5, I have to multiply the left side by 6 over negative 1/5. And so our 6's reduce, our negative 5's reduce, and we get our y by itself. That was the whole point. I could say 3 goes into 6 2 times. 2 times 2 would give me 4 here, and negative 5 over negative 5. A little bit of work there, but don't get wigged out when you deal with those fractions. Okay, here when I have negative 2 times w, I need to get that negative 2 to reduce with a negative 2 down here, and a 1 up here is what I'm going to have to deal with. That's my reciprocal. If I multiply that side, the right side, by negative 1/2, I have to multiply the left side by negative 1/2. And it doesn't matter if I write my negative down here, if I put it up here, just saying the whole fraction is negative. So our negative 2's would reduce, and I end up getting w by itself, and then I would have negative 13/2. Again, you can see I put the negative up here. Why didn't I put it down there? It doesn't really matter. The negative, I only have one negative in this. It doesn't matter if I write it in the numerator or the denominator out front. It's saying that fraction is negative. Okay, so that's using, the approach of the multiplicative inverse. But if you come down here, you can kind of think through a shortcut, and this is what most students are going to want to rely on. I know I myself do this as well. I want you to think of the multiplicative inverse by asking, how do we undo multiplication? We do that by dividing. Dividing and multiplying undo each other. And how do we undo division? Multiplying undoes division. So we kind of think that through as we're looking at this, and you ask yourself a little bit different question. In other words, I've got 3p is equal to 27. You ask yourself, what's the connection here? This is multiplication, and we undo multiplication with division. So I could write a 3 underneath here to notate that I'm dividing. I'm now saying 3p divided by 3. If I divide the left side by 3, I'm going to divide the right side by 3. So my 3's reduce, and I end up with p is equal to 3 goes into 27 9 times. So that would be our solution on that one. A lot of times students like that approach better. I myself also like that approach better. It's simpler. There's less writing down. You're not going to, you know, you're less likely to drop a negative and so forth if you just write that and deal with, think about undoing multiplication, undoing division. Okay, here we've got 10 is equal to m over negative 3. In other words, that's saying m divided by negative 3. So how do we undo that division? We would need to multiply by negative 3. That would be like multiplying by negative 3 over 1. So our 3's would reduce there. If I multiply the right side by negative 3, I have to multiply the left side by negative 3. So I end up with negative 30 is equal to m. Here this is saying x divide by negative 2. We undo division with multiplication. So I want to multiply this side by negative 2. I'd mean that I'd multiply this side by negative 2. This would reduce here, and so I'd have x is equal to negative 14. And I'm afraid my work looks like it's running into each other here. Okay, so here would be our solutions here. This next one, I could go ahead and multiply each side by 3. Undo that division with multiplication. So this reduces. So I have m is equal to 36. Now this one's a little weird, and I'm going to combine the shortcut that we're talking about as well as one of these concepts that we used here. How do we deal with that negative? So I've got negative y divide by 5. Well, that tells me I want to undo that division to isolate that variable. I want to undo that division by multiplying by 5. So if I multiply the right side by 5, I multiply the left side by 5. Now, I also want to get rid of that negative. And if you go up here, when we looked at this and we wanted to get rid of that negative, we multiplied by negative 1. So I want to go ahead and multiply by a negative. So that 5 that I'm multiplying by, I'm going to make it a negative. So I'm going to go over here and do the same thing. And let's see what happens. So my 5 and my 5 reduce. A negative times a negative gives me positive y. That took care of a lot of problems. And then I've had negative 5 times 1/8 would give me negative 5/8. There's a lot of processing in there. So we're going to get a chance to do that again over here. I've got negative p divide by 2. I undo that division by multiplying by 2. If I multiply this side by 2, I multiply this side by 2. Now I'm going to think about, I want to get rid of that negative. And we saw up here that if you wanted to get rid of a negative variable, you'd multiply by a negative 1. Well, I'm just going to make this a negative 2. If I multiply this side by negative 2, I have to multiply this side by negative 2. This would all reduce. My negative times negatives give me positive p. Negative 2 times negative 16 gives me positive 32. Now technically in all of these, I should go ahead and take this number, put it back in the original, just to double check it. I feel like my video went kind of long there as it is, so hopefully you get a chance to practice that, and then the next video we will do both the addition principle and the multiplication principle together.